All right, welcome back again, everybody. Today we're doing section 16.5, which is all about curl and divergence. We actually talked about curl quite a bit in the last section, so that part should go relatively quick. Then we're going to explore divergence, which is another very important property of vector fields. So let me get the slides going. Here we go. Good news is this lecture should be a little bit shorter, in part because we spent so much time talking about curl in the last section, or sorry, the last section. So it should be a little bit shorter, but here we go. Here's the overview. We're going to revisit the concept of curl. We will talk about divergence and get some intuition for divergence, talk about curl and divergence in general. We will talk about the Laplace operator, which I actually introduced way back in section, oh geez, I don't know, something in chapter 14. And then we're going to take a look at the vector forms of Green's theorem. So we got Green's theorem in the previous section. Now we're going to look at the vector forms of Green's theorem, and that will actually kind of lead us to seeing Green's theorem as a generalization of the fundamental theorem of calculus again, and how that's going to extend up to the divergence theorem being a generalization of the fundamental theorem of calculus. So let's get started. Just revisiting curl, so if you remember from the last lecture, this is the definition of curl. If you've got a vector field f with component functions p, q, r, then the curl of f is its own vector field on R3, and it's defined as this vector right here. So just a reminder that curl is a vector, and it's a vector field because it's giving you an amount, or not an amount, it's giving you a vector at every possible point in R3 or whatever region you're considering. Right. So in the last section, we got an intuition for what curl is, and we looked at some animations on the Math Insight website. And we also saw how Green's theorem relates to curl, just to give us a deep understanding of what's going on there. Now, in this section, we're going to see how we can express it using the cross product and reintroducing a bit of notation and also abusing it. So abusing some notation, but in this case, again, the abuse of notation is extremely suggestive and extremely helpful and extremely meaningful. So here we go. First thing we're going to do is we are going to define the vector differential operator given by this symbol and pronounced as del. And it is quite literally just a vector of this. So it's a vector that consists of the partial differential operators with respect to x, y, and z, right? Um, so what this operator is describing is it's describing the act of taking partial derivatives of a function and producing a vector where the partial derivatives are the component functions. Okay. Uh, if you've not heard about operators, I know I did talk about them in the past, and I know I did in these lectures. You just want to think about this as a function itself. It's a function that is taking in another function and it's producing a result. So when you view these things, when you view these components, you need to think of them as functions themselves. And what they are doing is this function here is computing the partial derivative of another function with respect to x and giving you that result. So the intuition I like to use is this. Think about the good old standard function notation from when you first learned about it back in algebra, right? F is the name or the rule of the function. F is the thing that says what to do to whatever you put into it. X is the input of the function. So you throw x into this function, f, and it does something to x, and the output is f of x. Same thing here. This is the function itself. This is the function itself. This is the function itself. It's doing something to whatever you put into it. Now, this is a function itself. And this function is saying, take the partial derivatives of whatever you put into me with respect to x, with respect to y, with respect to z, and produce a vector of those results. That's essentially what it's going to do. All right. Yeah, so del itself is a vector consisting of those partial derivative operators. These are the operators. That's what's going on. If the input of this is a scalar function, then what's nice is del is literally saying to take the gradient of that function. So it naturally agrees with the context in which we've seen it in the past. That's what's going on. All right. Now, more specifically, we can redefine this in terms of an operation process. So del f, maybe I should emphasize it as saying this, del of a function f is going to give you this. It's going to give you, well, it's going to do this. Maybe I should put that in parentheses too. It'll give you the partial derivative of f with respect to x, y, and z, and it will give you those results, this, and this, put them into a vector, and it's quite literally the gradient of f. So in some senses, this is kind of a natural generalization of this idea using this symbol. That's really what it's doing. Okay, so what's nice about viewing this thing as a vector is that it opens itself up to other operations. So this is where things get interesting. We're going to view this as a vector itself. And if we think of it as a vector with those partial operator components, then what we can do is we can actually consider things like the cross product of del with a vector field. And that's what we're going to do now. So remember we had that determinant formula for a cross product, this guy right here? So let's look at what it looks like when we cross del and f. So I, j, k are the basis vectors. Here's del, and then here's f. And just use the good old determinant process, right? Where you like cover this, you get that. Okay, cover this, do the determinant there, you get that. Cover this, do the determinant here, you get that. But lo and behold, that is the curl. That's the curl of f. This is quite literally the curl of f. One small little thing I'll point out, maybe some of you kind of like, furrowed your brow or squinted your eyes. Remember, normally when you're computing the determinant, the sign would alternate as you went along. Well, it does. The sign does alternate as you go along. But when you do the actual calculation, you'll see that these are switched. And so when you distribute that negative into to both of these terms, it'll give you the proper order for the curl. Long story short, quite literally, the curl of a vector field is del cross f. So it's a very compact way of viewing it, and it's a legit way of viewing it, and it gives you a quick way of computing. So on that note, guess what you get to try? Here, I want you to try this one on your own using that determinant notation. So find the curl of f if this is f, all right? You can think about it for a moment. Then, as always, you should say something out loud to your friends, to your family, to your dog, your cat, to yourself. And then try to compute it. See if you can compute the curl using that new notation we got. All right. Okay, let's do it together. The good news is this is a pretty algorithmic process. You're just gonna throw those vectors into a determinant and then compute the determinant, and it will give you the curl. So here it is. Here, remember, curl is del cross f. Here is our determinant. Here are the component functions of our vector field f. And remember now, what we're doing is we are viewing this, maybe if I do this for a second here. This is why it's kind of an abuse of notation, but it's a proper use of the notation in another way. If we cross this, when we do this product, quote unquote, we're not really doing a product. What we're actually doing is we are operating on negative y squared with this partial differential operator. So this is where the abuse of notation is coming in. We're not actually doing a product. What we're doing is we're doing an application of a function. That's what we're doing. So instead of it being a multiplication, it's an application of a function. In particular, it's the application of this function to that one. So that's what I've got pictured at the bottom. So I'm going to do the partial derivative with respect to y of negative y squared minus the partial derivative with respect to z of xyz times I, and then boom, 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 same thing here. So when you see these multiplications, they're not multiplications, they're function applications. There you go. But same thing here. This applied to this minus this applied to this. Notice the sign is negative here because we're just using the determinant notation. That's it. Then this, wait, I lost myself. That one. Oh yeah, so this applied to this, and then this applied to this. Then you can compute those actual partials, and you'll get these results. Simplify, and boom, you get the curl. You get the curl. So cool. It's so quick and so cute. All right. Now, now we can actually define what an irrotational vector field is. So if the curl of your vector field is the zero vector at every point, then your vector field is called irrotational. So in other words, it doesn't matter where you put the ball is not going to spin. So if you fix the ball at any point in your vector field, you get no spin on the ball. That's called irrotational. That's an irrotational vector field. There was an example of that in the Math Insight on the Math Insight website that I cited in the previous lecture. So you can look at that example again. Now, what we're going to get is we're going to get a theorem that is very similar to what we saw previously. This is it. If F is a conservative vector field over R3 that has continuous second order partial derivatives, then the curl of F is 0. That's what this is saying. Do I mention it later? Let me see. I do mention it in a couple of slides, but maybe, yeah, I'll save it for 2 slides from now. Let's prove this. Let's prove this real quick. If F is a conservative vector field over R3 with continuous second order partial derivatives, then the curl has to be 0. The curl of F has to be 0. The proof is actually very quick and very straightforward. It's a consequence of Clairaut's theorem, but here it is. Since F is conservative, by definition, there's a potential function F such that the gradient of F is equal to bold F. Now we can use that determinant notation to compute the curl. So the curl of F is the curl of the gradient of our potential function, which we can now write as del cross del F. In our determinant notation, it's this. And then you go through and you calculate the determinant. So do that, apply this to this, apply this to that, take the difference, and then work your way along. And you'll get the same thing, like so. However, by Clairaut's theorem, these things are equal to each other because basically the mixed second partial derivatives have to be equal because they're continuous. So since these are continuous, this is equal to that, you get 0. And this is equal to that, you get 0. And this is equal to that, you get 0. And that's the 0 vector. There it is. So if you've got a conservative vector field, the curl has to be 0. That's what this is saying. Now, kind of like before, the converse of this is not generally true, but it is true on simply connected regions. And so this is kind of the big theorem right here. If F is a vector field defined on a simply connected region, for example, R3, where the curl of F is 0, and whose component functions have continuous partial derivatives, then F is a conservative vector field. That's what it is. So it's not too much of an ask to get a conservative vector field. You just need to be looking at a simply connected region, and you need the curl of F to be 0. And then you need these component functions to be continuous. And so, I'm sorry, the partial derivatives have to be continuous, and that will give you a conservative vector field. Maybe some of you are kind of seeing this as you read these statements a bit, but we actually proved the 2D case of this in the previous section. So this was the one, wait, was it section 16.4 or 16.3? It was one of those two. But remember before I was talking about like the K component of the curl, and we proved this result for the K component of the curl. And it was basically that if all these things held true and the K component of the curl was 0, then you had a conservative vector field. It's the same thing here. Actually, that was section 16.3. Yeah. So we proved that, or we stated, that's right, that's what it is. We proved it in, yeah. So I stated the 2D case in section 16.3. We proved the 2D case in section 16.4. And now we are looking at the 3D case. However, the 3D case, actually, the proof of it requires Stokes' theorem. So we're going to omit it for now. Not going to prove it for now, but it's basically the three-dimensional analogy of the results that we saw in the previous 2 sections, right? And again, one thing that's nice about this theorem is that it gives us a simple way of determining if a vector field is not conservative, right? If it's not conservative. So you try this out. I want you to show that the vector field given by these component functions is not conservative, right? So ponder this one for a minute. Think about it. Okay, and now say something out loud about what you might try, what you might check. All right, now compute it or do your calculations and see what you get. And we'll do it together in a moment. All right, here we go. So we need to show that this vector field is not conservative. Okay, not conservative. So in the previous example, we actually computed the curl of this vector field, and the curl was not 0. So because the curl is not 0, our function cannot be conservative. That's it. That's pretty much it. There you go. Notice this is on a simply connected region as well, so we're all good there. Okay, so that kind of ends our discussion of curl for now. Now we need to go to a new concept called divergence. So this is another very important property of vector fields. And again, we're going to see how this abuse of notation can really help us again. I realize these are abuses of notation, but the results are very natural. So that's why we allow ourselves to do it. And it's not too much of a leap to change something like multiplication into a function application, right? The intuition follows, the mathematics follows, and everything works out nicely. So here's the definition of divergence. Let's say you have a vector field given by these component functions, we'll say on R3, and we're going to suppose that the partial derivatives all exist. Then the divergence of f is the scalar field of 3 variables defined by this sum. So what we're doing is partial p partial x, and adding to that partial q partial y, and adding to that partial r partial z. And that's what we're calling the divergence of f. All right, I think I mentioned it here. It's in a couple of slides. Maybe I'll mention it now. So here I'm describing the divergence on a vector field in R3, but you can actually do the divergence of a vector field of any number of dimensions, any number of dimensions. It just continues. It really just continues on. It's not too hard to generalize. So here's just a repeat of that formula. Now, because we are treating del as a vector, we can actually rewrite this divergence formula in terms of del. So del was this vector of the partial differential operators. So we can actually write this expression here as the dot product of del and our component functions p, q, and r. So this literally is this dotted with this. So we can express the divergence of f as del dot f. And there we go. How cool is that? There we go. The divergence is just the dot of del and f. Pretty cute. So what is this thing really measuring? So what is the divergence? What are we actually talking about? You know, who cares that we have this thing that we can write as a dot product? What is this? What's the point? So intuitively, what the divergence is measuring is the tendency of a particle to move away from a point x. You can think of it like that. So let's say you've got a point in a vector field and you wanted to drop a ball at that point. The question is the ball going to move away from that point or toward that point? That's kind of what it is, roughly speaking. So it's a tendency. It's a tendency for things to diverge, and that's why we call it the divergence. How does this make sense more mathematically? If you look at this sum, the sum here is the sum of the rates of change of the components of f in the respective basis directions at any point. That's what it's doing. So partial p partial x, partial q partial y, partial r partial z, those are just the rates of change of those components in those basis directions. That's what it's doing. So if the sum of those is a positive number, then that means particles have a tendency to move away from that point or outward from that point. They diverge, they flow away. If this sum is negative, then that means that particles have a tendency to fall into or fall toward that point. That's what the divergence is telling us. If it's positive, you're going to flow away. If it's negative, you're going to flow in. That's what's going on. Yeah, so this is what I mentioned a moment ago. Unlike curl, divergence can be calculated for a vector field over Rn for any dimension n without the need for a more general theory of calculus. So remember, curl for us in this class is only defined on three-dimensional vectors or vectors with three components, okay? Divergence can be defined for any number of dimensions, and you don't need a more general theory of calculus. You don't have to talk about exterior algebra. You don't have to generalize the notion of like a differential form and that kind of stuff. So divergence you can generalize naturally. Also, just a reminder, curl is a vector. So curl is a vector and divergence is a scalar. And what's cool about our abuse of notation here is that this actually jibes with the definitions of the dot product and the cross product, right? Remember the cross product gave you a vector, right? And in this case, this is the curl vector. And the dot product gave you a scalar. And in this case, this is the divergence scalar. So this notation abuse is really, really helpful. It's really handy. Another thing I should point out, I didn't point it out earlier. Let me do this before I go to that last little bit. Yeah, remember this proof? We were proving this one, right? Conservative vector field, then the curl is zero, right? If the curl is not zero, you can't have a conservative vector field. Well, check this out. If you think back to chapter 12, what did you get when you crossed a vector with itself? If you did like v cross v, you remember? Think about it for a sec. Right. A vector cross itself gave you the zero vector, right? So again, this particular abuse of notation is very, very fruitful. This is going to be zero. It's going to be zero. You're going to end up getting zero. So it jibes with that. Where was I? Back to here. Okay. So now this is a point where we need to take a pause, or maybe a transition, I will say. At this point, I would like you all to pause this video, and I want you to watch this required supplementary video by Grant Sanderson on his 3 Blue 1 Brown channel. And it's the video on curl and divergence intuition. So for real, what I want you to do now is I want you to pause this lecture, and I want you to go watch this video instead. You don't need to watch the entire video, but just watch it until you can get a visual intuition for what divergence and curl is, because this video is just phenomenal. It should give you a really, really nice understanding of it. All right? So you do that. I'm going to hang out here for a minute. All right, welcome back. So I hope you liked that video. I hope divergence and curl makes a lot more sense to you now. If you have that intuition, it's going to carry you very, very far in the future. Remember, the intuition is kind of what guides the mathematics, and then the mathematics saves us when the intuition fails. Okay, so let me do this. All right, let's do this. So using that new divergence formula, I want you to find the divergence of f of this vector field. Think about how you would do it. Kind of just gave you the big hint. Say something out loud about how you would do it. And then work it out. Shouldn't be too difficult. Should be a pretty quick calculation, and we'll take a look at it together in a moment. All right. Okay. So what we can do now is we can literally just dot del and f. So partial with respect to x of the first component of f, partial with respect to y of the second component, partial with respect to z of the third component, and this is our divergence. So this here is giving you a scalar field. So remember, this is a pointwise thing. So if you plug in any point x, y, z, this will give you the tendency of a particle to move away from that point or flow into that point. That's what it's doing right here. Okay. All right, so back to divergence on its own, let's take a look at this theorem. So if your vector field F is a vector field on R3, and P, Q, and R are C2 functions, that means continuous second order partial derivatives, then the divergence of the curl of F is 0. So divergence of the curl of F is 0. What this is really saying is that the tendency of a particle to move away from the curl vector is 0, as long as these are C2 functions. That's really all it is. The proof is very straightforward. It's very quick. Here it is. Again, it's Clairaut's theorem, showing up again over and over. What is the divergence of the curl of F? We can use our del notation and write it like so. This is the curl of F, which we can compute, and then we're going to dot the curl with del. So these are the components of the curl vector, and then when we dot them with the components of the del vector, we get this. Now we can apply these partial derivative operators to the individual terms. We get this. But again, because these partials are continuous, these second order partials, the mixed partial derivatives are equal to each other. So this will cancel with this, and this will cancel with this, and this will cancel with that. You get a whole bunch of zeros, which adds up to 0, and that's it. So that is an algebraic proof that the divergence of the curl is 0. Maybe a more geometrical proof is this. Remember what you know about cross products? I think I actually put this as one of my questions on the first exam. This vector that you get with the cross product is orthogonal to both of the factors of the cross product. So this is orthogonal to both del and F. So in other words, if they're orthogonal, that means the dot product of this with del or with F is 0, which is what we just proved. So once again, this all jives with everything we've seen in the past. All right, so now that we have a definition of divergence, we can define what it means to be an incompressible vector field. Simply put, if the divergence of your vector field is 0, then F is said to be incompressible. Nothing's flowing in, nothing's flowing out. Another word for this is your vector field has no sources or sinks. Sources or sinks. So by definition, a source is a point where the divergence is positive, stuff is flowing out. That's a source. Things are coming out of it, right? A sink is a place where, or a point where the divergence is negative. Things are flowing into it. Sources and sinks. For those of you that take differential equations, partial differential equations, you will study sources and sinks, but intuitively that's what it is. So if you've got a source, that means there's a point where stuff is flowing out from that point. And if you've got a sink, that means there's a point, or if you got a sink somewhere at a point, that means stuff has a tendency to flow in at that point. Now, if no such points occur anywhere in your vector field, then your vector field is said to be incompressible. Incompressible. Okay. All right, so we're nearing the end here. Now I want to take a quick look at the Laplace operator. I already introduced the Laplacian earlier on in the course. I think it was, oh man, I cannot remember the section. It was in chapter 14 when we talked about partial derivatives and higher order partial derivatives. But we're going to revisit the Laplace operator because the Laplace operator shows up a lot. So hopefully this is a little bit familiar, but if we compute the divergence of a gradient of a vector field, we get this. The divergence of del F, but remember we can write the divergence as dotting the vector field with del. But then we can rewrite this as dotting del with itself and then applying that to the function f. And this particular operation, this particular expression occurs so often that we denote it as this this triangle instead. And it's defined as del squared, which is just del dot del. That's what it is. All right. Oh, here, let me do this real quick. Okay, so this thing is called the Laplace operator. And the reason it's the Laplace operator is because Laplace's equation is literally this. You're going to add up all the second order partial derivatives, and Laplace's equation says that the sum of all of those second order partial derivatives is 0. So in other words, this is equal to 0. I mentioned this earlier as well, but the solutions to this equation, meaning the functions that satisfy this result, those are called harmonic functions. So those are functions for which the tendency of a particle to move away from the gradient at any point is 0. That's another way of interpreting these things. That's what a harmonic function is. Particles don't want to move away from the gradient for these harmonic functions. All right, now that being said, let's move on to the vector forms of Green's theorem. So these are basically just re-expressions of Green's theorem using vector notation instead. And now that we know what curl is and divergence is, and we have these notions of what they do, we can re-express Green's theorem in a couple different ways that give you a little more insight into what it's actually describing. So if you remember from section 16.4, or 16.3, should say like or 16.3, the what I called the k curl of your vector field is just the k component of the of the uh, of the vector of the curl vector, right? So you take the curl vector and you dot it in the k direction, or with the k basis vector, and you get this, right? So this was the expression that occurred in Green's theorem, and we looked at how it was related to curl in the previous sections. So because of that, we can express it directly as this. So this is what I didn't say back in, section 16.3 or whatever, right? But this is the same thing. So this is Green's theorem restated, but now it's in vector form. So if you want to do the line integral of a vector field around a curve C that encloses a region, you can do the double integral of the curl of f dotted with k, curl of f dotted with k, over the region D. That's the K curl, right? Um, yeah, this is exactly what I was saying before. And this is exactly what I was saying before. So in other words, the circulation of the force field around C is the sum of the circulation, the microscopic circulation within the region. Just writing it in terms of a vector. That's it. Or I should say the dot product of a vector. Right, now we're going to get another form, and this is actually going to lead us more to something related to the divergence theorem. So suppose C is given by a vector equation R of t, then we can compute the unit the unit tangent vector using same techniques that we learned back in chapter 13. So t of t is this. We're just going to divide r prime of t by its length. That's what this is, dividing r prime by its length. Then the outward unit normal vector is given by this lowercase n. And this is the normal vector, but it's pointing in the outward direction. You might remember that the normal vector given by capital N points to the inward direction. This one is pointing in the outward direction. So I want you to note here that these components are switched and the sign is changed. So if you've got like some curve, right, this vector is pointing out instead of in, right? Like, yeah, I'll just leave it at that. You can verify that on your own. That computation is left as an exercise, but that's what it is. So now we're going to do this. If we want to compute, oh, wait, hold on. Lost my train of thought here. Just this. Am I? Hold on a second. Give me one moment here. All right, there we go. Sorry about that. So check out what we're going to do here. So we're going to compute this line integral, but what we're going to do is we're going to add up the outward normal component of the force field along the curve itself. And we're going to do this with respect to arc length at first. But using our parameterization of the curve, r, we can convert ds to the length of r prime t dt, right? And then now what we're going to do is we're going to look at what f dot n looks like. So f is our vector field, n is our outward normal unit vector, and this is what that dot product is going to look like so. It looks a little bit messy, but really this is just p with our parameterization in there, and then you have y prime from the outward unit normal vector, and then here is q with our parameterization subbed in, and then this factor is coming from the outward unit normal vector, and then dividing by the length, of course. But this will simplify into something nice. So the r prime t lengths are going to cancel. And then what you're left with is this, right? Simplifying things, writing them in terms of these differentials instead, we get this, right? This is dy and this is dx. Okay, now I'm just going to swap the order a little bit. So I'm going to move this over here and you get this. But check this out. Check this out. By Green's theorem, we can rewrite this as a double integral. We can write this as this double integral right here. And then these negatives are going to cancel each other out. And then what you're left with is partial p partial x plus partial q partial y, which is the divergence. So this is the divergence of your vector field F. And now we have this result. So this is equal to this by Green's theorem. Boom. So this is another vector form of Green's theorem. But in this case, what we're doing is we're relating it to the divergence of F instead. So what this says is that the line integral of the normal component of F along C, instead of the tangential component, is going to be equal to the double integral of the divergence of F over the region D enclosed by C. So it's a little bit different because now we're looking at the normal components instead of the tangential components, but you can see how they're related to divergence and curl. So if you look at these are these two results. So this is what we had derived earlier. Notice here we're looking at the tangential component of the force. Here we're looking at the outward normal component of the force. And Green's theorem relates these two ideas. So more intuitively, the outward flux of your vector field F over the curve C, that's what this is giving you, like the outward flux over the curve C, it's equal to the sum of the divergence within the region that C encloses. We're going to explore that more later when we talk about the divergence theorem and Stokes' theorem and so on. But those are the results. Yeah, here you go. Adding up the tangential component gives you the macroscopic circulation, and this is how it relates to the microscopic circulation inside the region. Adding up the outward normal component of the force is related to the divergence within the region, like so. Just very clean, beautiful results. It's really, really nice. And we'll see these things again later. All right, on that note, let's play. All right, so I hope this was a fun lecture. I hope it was a little, I'm glad it was a little bit shorter, a little cleaner. I'm excited to work with you about this stuff. If you have questions, let me know. I'll stop rambling there. Thank you again, as always, for watching, and I will see you next time.